This is the lecture video for Chapter 10, Chemical Bonding 1, the Lewis Model. Here we're going to take a look at the three different types of bonding: ionic, covalent, and metallic. We're also going to see how to draw these molecular structures using the Lewis model. It's very important to take a look at the periodic table throughout this chapter, just so you can understand the concepts a lot better. The basis of treating diseases and disorders is to understand the molecular geometry of the thing that's causing the illness, and then developing effective treatment based on that geometry. Here, HIV protease is the enzyme that causes AIDS. So an effective treatment would involve an inhibitor, which binds to the enzyme's active site, which disables it. Treatments like this don't work if the molecular structure isn't compatible. Now that it's 2021, we are still in the middle of the COVID-19 pandemic, but we're not focusing on the different types of treatments for patients who are infected with COVID-19. Now we have vaccines that would help protect people from the virus. But a vaccine won't be effective if the antibodies that are being created are not compatible with the geometries of the antigens that are found on the virus. After going through different concepts in this chapter, you'll see why we can't just throw different elements together and try to form a molecule. There are rules and trends that we have to follow, which are all based on observation. We could also use what we learned here to figure out the shapes of these molecules or the geometries of these molecules. And then we would understand the physical and chemical properties based on these shapes. And we'll see more of that in the next chapter. There are several different bonding theories, but in this chapter we're only going to understand the Lewis bonding theory. You might have learned about this theory before, back in high school. You may have drawn Lewis dot structures already, but here we're also going to take a look at polarity and some chemical and physical properties of these different molecules. Let's think back to the chapter with all the different types of energies, like light energy, chemical energy, kinetic energy, but let's specifically take a look at potential energy. Remember that if a system has a high amount of potential energy, that system is very unstable. As the potential energy lowers, then the system becomes more stable. Well, the same idea goes with chemical bonds. Whether it's atoms or ions coming together to share or transfer electrons, those bonds that are being formed would lower the potential energy of the system, and it would make that system more stable. Now, you're not going to be calculating potential energy or anything like that, but you do have to understand that there are repulsions and attractions taking place. Remember that electrons are negatively charged. Nuclei are positively charged because of the protons located in nuclei. If you take a look at your periodic table, and you could tell where the metals are, where the nonmetals are, then you'll know what type of bond exists between two different atoms. So with an ionic bond, electrons are being transferred, and the types of atoms involved are metals and nonmetals. If you're just looking at two nonmetals, then electrons are being shared, not transferred, and you're looking at covalent bonds. And if you're only looking at metals, Well, that's easy enough. The type of bond is metallic and electrons are being pooled in that metal. Here's a really nice picture showing the three different types of bonding. We've got ionic bonding here with our crystal lattice of alternating cations and anions. For covalent bonding, you see individual H2O molecules. And with metallic bonding, all of these are Na plus ions because we're looking at a sodium piece of metal. And electrons are going to flow through this metal, and we call that the electron sea. Don't forget any of the periodic trends that you learned in the previous chapter, because we are going to see it again in chapter 10. So you should remember that metals have low ionization energies, so it'll be very easy to remove electrons, and that's why they become cations. When you take a look at nonmetals, again, remember they have very high electron affinities. So think of the halogens. They want to gain electrons to have the noble gas configuration, and so they become anions. Once this transfer of electrons happen, then these oppositely charged ions are going to be attracted to each other and form ionic bonds. With covalent bonds, electrons are being shared, not transferred like in ionic bonding. So here, the bond is actually going to occur between the two nuclei. If we just had two nuclei very close together, there's going to be a repulsion. So having the bond directly between the nuclei would help offset that repulsion between the nuclei. So this middle arrangement here, if we're going to throw in potential energy, this arrangement would be the most stable and thus have the lowest potential energy. Looking at metals again, they have low ionization energy. So if we're looking at metallic bonds, we're only considering metals, not a mixture of metals and nonmetals. So if you have a block of pure silver, let's say, then there would be an electron sea found throughout that silver piece of metal, because all of those silver atoms are going to lose electrons. So electrons will be able to flow through that piece of metal. And that should make sense because metals are very good electrical conductors. Take a look at this word here, delocalized. You're going to be seeing that word a lot. Again, that's telling you that electrons are not stuck on one particular atom. Here in this case, it's going to move throughout that piece of metal. Let's test your understanding. So which compound is most likely to contain ionic bonds? Here are your three choices. So please pause the video, take a moment to think about it, and when you're ready for the answer, click play. Letter C is the only one that has a metal and a nonmetal. And we know that metals and nonmetals are the ones that form ionic bonds. Choices A and B are molecules, and there are covalent bonds between these atoms. In this chapter, valence electrons are more important than core electrons, because it's the valence electrons that are doing the bonding. So if you think back to previous chapters, there are two ways for you to figure out how many valence electrons an atom would have. You could either write out the full electron configuration and figure it out from there, Or you could take a look at the periodic table, and if we're looking at main group elements, it'll be very easy. Take a look at the column number that element is found, and then that'll tell you how many valence electrons that element would have. For transition metals, it'll probably be a good idea to write out the electron configuration for them, because don't forget about the S block. Those electrons would be removed first, and then the electrons from the D block. Here's how you would draw the Lewis dot structure for oxygen. It's found in the 6th column, so it has 6 valence electrons. There is no formal way in drawing out the dots, but I know some people who would prefer going around the elemental symbol in a clockwise fashion and just adding dots that way. Okay, first you would add in the 12 o'clock position, then 3, 6, 9, and then go back to 12 to add the 5th electron, and then 3 for the last electron. So in this manner, you could see that there are 2 pairs. There are 2 pairs of electrons. Okay, they don't have to be in the 12 and 3 o'clock position. You could switch it up. I feel like it's the same thing, but just make sure that for oxygen, you show that there are 2 pairs of electrons. You could follow these rules if you want to, or you could follow this arrangement here. You know, as long as you have the correct number of valence electrons, then I feel like it's fine. Drawing out the pairs of electrons, I honestly feel is more important when we start drawing out actual Lewis structures of different molecules. A couple of slides ago, we saw that oxygen is found in the 6th column of the periodic table, so it has 6 valence electrons. Now we have N2. So how many valence electrons would N2 have? Go ahead and pause the video, take some time to figure it out, and when you're ready for the answer, click play. Okay, so the answer here is 10. We know that nitrogen is in the 5th column, so one nitrogen would have 5 valence electrons, but because we have N2, we have another nitrogen involved, so 5 plus 5 equals 10. Now we have water, H2O. So how many valence electrons would H2O have? Pause the video, think about it, and when you're ready for the answer, click play. Okay, so the answer is 8. We have 6 valence electrons for oxygen. If you look at the periodic table, you'll see that hydrogen would have 1 valence electron, but because we have 2 hydrogens, we need to add 2 to the 6 from oxygen so that we get 8 valence electrons for H2O. Let's review a little bit. Taking a look at your periodic table, what is the Lewis symbol for silicon? So pause the video, look at your periodic table, and when you're ready for the answer, click play. You should see that it is in the 4th column, so it should have 4 valence electrons. So our answer here is letter D. Remember when metals and nonmetals form ions. they are obtaining a noble gas configuration. So here we see potassium, a regular potassium atom, neutral atom, and K+. So we see that it lost one electron and came from the 4s orbital. Normally you would not write 4s0, but they put it here just so you know which electron was removed. So what's left over is the set of 8 electrons found in the 3rd energy level. So here is our complete octet, or our noble gas configuration. This arrangement here is very stable. Don't forget that this configuration right here is the generic noble gas configuration, but it only represents the 8 valence electrons in the outer shell. The N represents the energy level, or the row number, or the period. And the superscripts represent the number of electrons found in those subshells. So please don't forget, when a system becomes more stable, the potential energy lowers. So when atoms become ions, certain number of electrons are gained and lost, so that in the end, that ion would have a noble gas configuration, which is very stable. So then we have something called the Octet Rule, where the outermost shell, or the valence shell, would contain 8 electrons. But there are some exceptions to this rule, and you have to memorize these exceptions. So some of them you've seen already. For hydrogen and for helium, you would see complete duets, so 2 electrons instead of complete octet. For beryllium, usually you would see it with 2 covalent bonds, or just 4 electrons. With boron, you would see 6 electrons. Now, if you take a look at the periodic table, for elements in period 3 or below, those elements can have expanded octets. So elements like sulfur and phosphorus, they could have complete octets, but because they also have a lot of empty d orbitals, they could have 10 electrons or maybe 12 electrons in their outermost shell. So here is the Lewis structure for KCl. KCl is an ionic compound. Electrons are being transferred, so here we know that potassium has 1 valence electron and chlorine has 7. So we're just going to take this 1 electron here and transfer it over to the chlorine. So now that we have a potassium ion and a chloride ion. Now, if you've learned about Lewis structures before, you probably would have drawn lines to connect 2 different atoms. Well, here's the thing. That line that you would draw, that line represents shared electrons. There are no electrons being shared here. They were transferred. So that's why you would have to draw the Lewis structure for an ionic compound like this. So please don't forget the charges. Here in this textbook, they have brackets around the anion. And the anion, you have to show all 8 electrons, showing the complete octet. Now let's try to figure out the formula for calcium chloride. and also draw the Lewis symbols for calcium chloride. Here are the Lewis dot structures for calcium and chlorine. You can see that they have their valence electrons, 2 for calcium, 7 for chlorine. Calcium would have to lose both of its valence electrons so that it could have a noble gas configuration. Okay, so one of these electrons is going to be transferred to this chlorine atom to become a chloride ion. Now what's going to happen to this electron? It's not going to float around anywhere. It has to be transferred somewhere. So we would need 2 chlorine atoms so that both electrons from calcium can be transferred. Okay? So you could see we only need 1 calcium ion and 2 chloride ions so that we can form our calcium chloride. Okay? What's important to remember is that ionic compounds are neutral. They are neutral. So the positive charge from the cation needs to equal the negative charge from the anion. So here for chlorine, we would need 2 of these ions so that the +2 can be canceled out by the -2, so that we would have a neutral ionic compound. You're going to do the same thing again, but this time between magnesium and nitrogen. Figure out what the ionic compound would be using the Lewis symbols. So please pause the video, draw out the symbols to figure out the formula for the ionic compound, and when you're ready for the answer, click play. Here are Lewis dot structures for magnesium and nitrogen. Okay, take note of the valence electrons. Okay, so you can see that magnesium needs to lose 2 electrons to have a noble gas configuration, but nitrogen needs to add 3 electrons to have a noble gas configuration, or a complete octet. Okay, now we have to make sure that we have the correct amounts of each ion so that we form a neutral ionic compound. Okay, going back to basic algebra, we would need 3 magnesium ions and 2 nitride ions. Okay, if we multiply these numbers here for magnesium, we would have a +6. When we do the same thing for nitride, we'd have a -6. So now when we bring these two together, we would have an overall charge of 0. So our formula would be Mg3N2. So at this point, we know why bonds form, and that's to lower the potential energy. We also know how they form because the ions obtain noble gas electron configurations. Now we can take a look at the different ionic compounds and the bonds that hold them together and rank the relative strengths of those bonds. But in order to do that, we have to revisit Coulomb's law. So it's E equals some kind of constant times Q1 times Q2 divided by R. Q1 and Q2 represent the charges, so here in this case it'll be the charges of the ions involved, and R would be the distance between those ions. So let's combine the periodic trends that we learned in the previous chapter with energy, specifically delta H. Ionization energy is the amount of energy needed to remove one electron from an atom. So here in our example, we have sodium metal, and we could see that energy is needed to remove that one electron. So this process is endothermic. With electron affinity, a nonmetal wants to gain an electron, and usually that is exothermic. And you see that here with chloride gas. So when we add these two values together, we are trying to form NaCl solid. So when we add these two values, we're supposed to get something that is endothermic, right? But through experimentation, we see that the delta H formation of NaCl solid is something that is very exothermic. Now, how does that make sense with the numbers that we have here? Well, there must be something missing in the process. The ions in an ionic compound are arranged in a crystal lattice. So what does that mean? Well, if you take a look at one Na plus ion, you'll see that chloride ions are surrounding it, and vice versa. So in this arrangement, the number of attractions for any ion in that crystal lattice will be maximized. And because of that, that system will be very stable. The potential energy will be really low. So when this crystal lattice forms, a lot of energy is released. Don't consider NaCl as just one molecule of NaCl, which is made up of Na plus and Cl minus. We already saw that ionic compounds form crystal lattices, so you'll actually have moles of Na plus and moles of Cl minus ions. The formula that you write down is actually an empirical formula. So that's the simplest ratio of positive and negative ions that would produce a neutral compound. Remember that ionic compounds are neutral, so you need to have the right amount of positive and right amount of negative ions to come up with something that's neutral in the end. The energy that's being released as the crystal lattice forms is called lattice energy. So this delta H value is always going to be negative because it'll always be an exothermic process. The higher the magnitude this lattice energy is, the more stable the ionic compound is. Now we have to look back at Coulomb's law again, and we could figure out how strong these bonds are based on the charge magnitude between the two ions and the distance between those ions. So we cannot measure lattice energy directly. We have to go through a series of steps called the Bourne-Haber cycle to form our ionic compound. And if we know all the other steps in that process, including the final summation step, then we could figure out the lattice energy for that ionic compound. Here is the Bourne-Haber cycle. We're trying to form an ionic compound, which is a salt, starting off with metal and nonmetal atoms. We have to turn them into gases so that they can go through ionization energy and electron affinity. So if we have all those values, then we can figure out lattice energy. So just for review, a metal atom would undergo ionization energy in order to become a cation. If we have a metal like barium, which would have a +2 charge in the end, it would have to go through 2 steps of ionization energy. For nonmetal atoms, they go through electron affinity. So again, once we have all of these delta H values, we can use Hess's law to figure out the unknown lattice energy. This is a very nice picture showing all the steps. Again, with Hess's law, we're taking a series of steps and adding them all together to have one overall reaction. And when we do that, we're also going to add up the different delta H values for each step. Now let's figure out the lattice energy for NaCl. So here are all our steps. We have our metal and nonmetal turning into gases. And then they go through ionization energy and electron affinity so that they can become ions. These ions then come together to form our ionic compound. Okay. So we're crossing out similar species that occur on the reactant side and on the product side so that we're just left with our final reaction. All that works out, so now we can figure out the lattice energy for NaCl. Okay, we put our unknown on one side of the equal to sign so that we could solve for it. We plug in our values, and here we can see a very large negative lattice energy for NaCl. Now that should make sense based on what we saw from the previous slide. The delta H value in the formation of NaCl was negative 411 kilojoules. So that missing piece was lattice energy, something that was extremely exothermic. Let's take a look at Coulomb's law again, so that we can understand the different trends in lattice energy. So if we take E to be lattice energy, we can see that it is inversely proportional to R, which is the distance between the two ions. As R increases, then lattice energy would decrease. Okay, so let's think back to one of our periodic trends, which is atomic radius, or in this case, ionic radius. As we go down the column in the periodic table, the size of the ion would increase. In other words, R would increase. So if you're looking at a large ion, there's going to be weaker attraction, because now these two ions are going to be further away from each other. So if there's weak attraction, then the lattice energy would be smaller. Here's a table of metal chlorides with their respective lattice energies in kilojoules per mole. We could see that the cations come from the first column because of the +1 charge. As we go down the column, the size of the ion increases. We don't have to take a look at Cl- because it'll stay the same regardless of the compound. So as the size of the ion increases, the distance between those ions would also increase. Now take a look at the lattice energies. If you just take a look at the magnitudes, you'll see that the lattice energy is decreasing. Or in other words, the lattice energy is becoming less negative. So the weakest bond in this set the weakest bond occurs in the cesium chloride compound. Taking a look at ionic charge now. Q1 and Q2 are directly proportional to lattice energy. So if those charges increase, then the magnitude of the lattice energy would also increase. Or in other words, the lattice energy becomes more negative. So if we see larger charges, so that's with calcium oxide, there's going to be a stronger attraction between these two ions, and so the lattice energy will become larger. So now taking a look at ionic charge and distance, ionic charge is more important of the two. So let's try and arrange these compounds in order of increasing magnitude of lattice energy. You have to take into account the charges and also the size of each ion, so then the distance. Okay, so please pause the video, take some time to figure out the arrangement based on size and charge, and when you're ready for the answer, click play. Okay, so this is the order, starting with KBr. Calcium oxide would be the one that has the highest magnitude of lattice energy, or in other words, it's going to be the most negative. And here are the actual lattice energy values. Okay, in the next slide, I'll show you how to figure out this arrangement based on charge and size.
So we need to put these four ionic compounds in order of increasing magnitude of lattice energy. For lattice energy, think of Coulomb's law, which is E equals some kind of constant times Q1 times Q2 over R. So charge matters and the distance between those charge matter. So we have to take into account those two things when we're putting these four compounds in order. So the more important characteristic is the magnitude of the charge. So we'll place these four in order of charge first. Okay, so now we got to look at each component of all the compounds and figure out what the charges are. So for calcium, it's a +2. Oxygen is -2. Potassium K, +1. Br is -1. +1 again. Cl is -1. Sr is +2. And again, -2 for oxygen. Okay. So again, increasing magnitude of lattice energy. The first compound that we write needs to be the smallest. So here we can write either KBr or KCl. It doesn't matter, because right now we're just looking at charge. So KBr, KCl, and then we'll write CaO, and then SRO. So now everything is in order based on charge. But now we also have to look at size. We have to take into account R. Okay, so now what we're going to do is we're going to divide this in half and look at each pair one by one. So KBr, KCl. We don't need to look at the Ks because the potassium is going to be the same size. We're going to look at our halogens. So take out your periodic table and see where Br and Cl lie in column 7. Br is lower than Cl. So thinking back to your trends, Br is going to be the bigger ion. So that means Cl is smaller. Now let's look over to our other pair, CaO and SrO. We don't have to look at oxygen. We're just going to look at calcium and strontium. Find them in the periodic table. They're in the second column. Which one is lower in the column? That'll be Sr. So that means Sr is bigger. All right, so now let's place these in order based on size. Remember, we're going in increasing in magnitude, so whichever one we're going to write first needs to have the smallest magnitude of lattice energy. But here for size, that means the bigger ion would have the smaller magnitude. So our order is KBr, then KCl. Then it's going to be SrO, CaO. This is our order.
Take a look at these 3 ionic compounds and arrange them in order of increasing magnitude of lattice energy. Please pause the video, work it out, and when you're ready for the answer, click play. Okay, here's our arrangement. Our calcium oxide is going to be the one that has the highest magnitude of lattice energy. Calcium has a +2 charge, oxygen has a -2. With our other 2 compounds, if we break them up, they each have a magnitude of 1, with K and Li being +1, I and Br being -1. Now, taking a look at Ki and LiBr, when you look at the periodic table, you'll see that K is lower in the column compared to Li, and also I is lower in the halogen column compared to Br. So in terms of size or radius, Ki would be the larger between the two. So here in our arrangement, it's the one that's going to have the smallest magnitude of lattice energy. Now take a look at this one. Which of these 2 would have the higher magnitude of lattice energy? So please pause the video, take a couple of moments to figure it out, and when you're ready for the answer, click play. Okay, so our answer here is MgCl2. Okay, we're really just going to look at the charges. So for chlorine, it'll be -1 for both compounds. Na is +1, but Mg is +2. So remember, ionic charge is going to be the one that's more important to look at compared to size. So here you could automatically say that MgCl2 would have the higher magnitude of lattice energy. Let's take a look at this bonding model versus what we actually see in reality. So with this theory, this Lewis bonding theory, in regards to ionic compounds, we're saying that these compounds should have really high melting and boiling points. Why is that? Well, lattice energy is extremely exothermic. It stabilizes the crystal lattice. So a lot of energy is going to be needed to break up these strong attractions between positive and negative ions. Now, what do we see in reality? It is true. Melting points for ionic compounds are very high. And the attractions between positive and negative ions are so strong that all ionic compounds are solid. They're in the solid phase at room temperature, which is about 20 degrees Celsius. Because of lattice energy, it would be extremely difficult to move these different ions out of place. So in other words, these ionic compounds would be extremely hard. And in reality, that's what we see. So if you take a large grain of salt and you try to squeeze it between your fingers, most likely that grain of salt will not break. But if you take a molecular solid like lard, that piece of lard would probably be deformed as you squeeze it because of its softness. Following the same logic, repulsive forces would occur if ions are moved out of place in the crystal lattice. So in order to reduce the amount of repulsive forces, the crystal would just break apart. And that's what we see in reality. So think of stepping on rock salt during the wintertime when you're walking on the sidewalk. You'd hear that rock salt crack if you apply enough pressure on it. If we're just looking at ionic solids, we know that those ions cannot move. They're stuck where they are in the crystal lattice. So, can ionic solids conduct electricity? The answer is no. Because none of the ions are able to move, electricity cannot flow through the ionic solid. Now, what happens if you melt that solid or you dissolve that solid in water? Would those two phases be able to conduct electricity? The answer is yes, because now in both states, the liquid and aqueous states, we have charged particles that can move throughout that state. And so because of that, those states can conduct electricity. Let's check for our understanding now. Use the ionic bonding model to determine which has the higher melting point, sodium chloride or magnesium oxide, and explain why. Please pause the video, read through all 4 statements very carefully, pick your choice, and when you're ready for the answer, click play. The answer here is letter A. So think about Coulomb's law with the charges. If the magnitude of the charges increase, then the magnitude of the lattice energy will also increase. So for Na and for Cl, the magnitude of those charges would be 1. So Na is +1, Cl is -1. For Mg, the charge for the Mg ion is +2, and oxygen is -2. So letter A is the only one that makes sense here. Now let's take a look at covalent bonding. The main difference between covalent bonds and ionic bonds is that covalent bonds involve the sharing of electrons. There is no transfer of electrons going on. So when we're counting complete octets for each atom in the molecule, we have to consider the shared electrons between 2 atoms. There are two types of electron pairs that we have to consider: bonding and lone pairs, which are also known as non-bonding pairs. So here we have the Lewis structure for H2O. We know from a previous slide that H2O has 8 valence electrons. We could see one bonding pair here between the oxygen and the left side hydrogen, and another pair between oxygen and the other hydrogen. The other 4 electrons constitute the 2 lone pairs that are found only on oxygen. So here we could see oxygen has a complete octet because we see 8 dots that represent the electrons. If we take a look at this left-sided hydrogen, we see that it has a complete duet. We're looking at these 2 electrons, even though they were used in the counting of the complete octet for oxygen. Because they're being shared, we could also use them to count towards the complete duet for hydrogen. If there is one bonding pair between 2 atoms, then we call that pair a single covalent bond. Now when we see that, we have to remember that there are 2 electrons in that bond. So again, looking at water, H2O, we see that there are 2 bonding pairs. I highly suggest that you draw out H2O like this, with the lines connecting both H's to oxygen, so that you could easily count how many lone pairs there are and how many bonding pairs there are. When 4 electrons are being shared between the same 2 atoms in a molecule, we then have a double covalent bond. Again, I highly suggest that you use lines to show the double covalent bond instead of the dots, so that you could easily see how many pairs are lone pairs and how many are bonding pairs. When 6 electrons are being shared, we now have a triple covalent bond. If you want to use dots to show which electrons are shared, make sure that you draw them very carefully. But I could understand if someone confuses this arrangement as a double covalent bond instead of a triple. Now, taking a look at this and going back to a previous question, how many valence electrons N2 would have? Our answer there was 10, because we're adding 5 electrons from one nitrogen and 5 from the other. You could count here in this Lewis structure that there are 10 valence electrons. Also, if you look at this nitrogen on the left-hand side, we could see that it has a complete octet. And the same goes with the other nitrogen. Let's take a look at the bonding model versus what we actually see in reality. So just like with ionic bonds, covalent bonds form for stability. And we could figure out stable combinations from complete octets. Now, there are some exceptions to this rule, but generally speaking, these atoms want to form complete octets. With hydrogen, we know that they form complete duets, and because of that, they form diatomic molecules, and the same goes with halogens. With oxygen and a couple of other elements, you could see a combination of single, double, and triple bonds. But the main idea is to achieve a complete octet. So why is water H2O and not H3O? Well, we saw this already. Both hydrogens have complete duets. Oxygen has a complete octet. And all the valence electrons have been used in drawing out this structure. With H3O, we are using 9 electrons here, but take a look at oxygen. Oxygen has 9 electrons, and that is very unstable, so this molecule actually does not exist. Later on, you'll see this structure here. This is a hydronium ion. This actually exists. You can see all the valence electrons are used, and oxygen has a complete octet. Same thing goes with hydrogen peroxide. Both hydrogens have complete duets, and the oxygens have complete octets. So it's only this structure here that's very unstable and does not exist. One difference between ionic bonding and covalent bonding is that covalent bonds are directional. There is no crystal lattice here when we're talking about covalent bonds. So when you write out the formula H2O or CO2, we know that you're talking about one molecule of H2O and one molecule of CO2. The melting and boiling points of molecular compounds are extremely low compared to ionic compounds. This is where we have to take a look at intermolecular forces and intramolecular forces in molecular compounds. So with the covalent bonds, the sharing of electrons, those are called intramolecular because they are found within the molecule. Intermolecular forces are found between different molecules. So generally speaking, the melting point of molecular compounds would be less than 300 degrees Celsius. But because of the variety of intermolecular force strength among molecular compounds, these melting points and boiling points vary greatly. And so because of that, we can see all 3 states of these compounds in room temperature. So for example, carbon dioxide, the carbon has 2 double bonds between the oxygens. So that's a molecular compound. That is a gas at room temperature. H2O would be liquid. Sucrose would be solid. So we could see the 3 different states of matter at room temperature, but all 3 of those compounds are molecular compounds. Here's a great picture showing the difference between intramolecular forces and intermolecular forces. So we have liquid pentane that's being boiled, so turning from a liquid to a gas. That's a physical change. These dotted lines here, they represent the intermolecular forces between the different pentane molecules. It's these weak intermolecular forces that break. They break during boiling so that these liquid molecules become gaseous molecules. The covalent bonds found within the molecule stay intact. If these covalent bonds actually break, then what we're going to be looking at would be a chemical change instead of a physical change. So with this physical change, the molecule is still pentane. Because there is a wide range of intermolecular force strength, there's also going to be a wide range of hardness in the different molecular solids. So if you want to think of sucrose, if you try to break the grains of table sugar, you'll see that they shatter, and you would need a lot of pressure to break those sugar grains. But if you had lard again, or any type of solid fat, those things are very soft, so they won't shatter when you try to put pressure on them. Because molecular compounds are neutral, and they don't break up into ions because of the sharing of electrons as opposed to transfer of electrons, molecular solids and liquids should not conduct electricity at all. So if you had pure water, which is neutral, electricity cannot move through that water. If more electrons are being shared between two atoms in a molecule, then the bond strength is going to increase as the number of electrons being shared increases. So we see that to be true in reality. The triple bond would be the strongest type, while the single bond would be the weakest type. But we cannot say that they are directly proportional to each other. So in other words, if you want to break a single bond, let's say that you need 100 kilojoules of energy to break that single bond. If you're trying to break a triple bond, we cannot say, all right, now you're going to need 300 kilojoules of energy to do that. We cannot say that because that is not the trend. We can only generally say that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. When more electrons are being shared between two atoms, the bond will be shorter. So with triple bonds, they would be the shortest type of bond, and single bonds would be the longest type. Now we cannot say that triple bonds are 30 picometers and single bonds are 90 picometers. We cannot make that very specific relationship. We can only just generally say triple bonds are the shortest and single bonds are the longest. Let's test what we've learned so far. So take a look at this statement here and say what is wrong with it. Atoms form bonds in order to satisfy the Octet Rule. So pause the video, read through the choices carefully, and when you're ready for the answer, click play. So atoms don't form bonds to form molecules just so they could satisfy the Octet Rule or have an expanded octet. Okay, that is part of it, but one of the real reasons that atoms form bonds is to lower the potential energy. They want to come together, they would form a very stable system, and when doing so, the potential energy gets lowered. It's the Octet Rule, this rule that we've sort of made up, and because of observations, we use this Octet Rule to help us figure out how atoms are going to bond with each other. Not all sharing is going to be equal in terms of covalent bonds. There are some elements that want to hog up the electron cloud, making one side a little bit more negative than the other side. And when we see that, we have a polar covalent bond. So think of a magnet with two poles, one on either end of the magnet. One side is positive, the other is negative. The same thing can be said with a covalent bond, a polar covalent bond. The atom that wants to hog up all the electrons, that side is going to have a partial negative charge, and the other side will have a partial positive charge. Here are three different ways in showing bond polarity. So the molecule that you see here is HF, hydrogen fluoride. This En represents electronegativity. So fluorine has an electronegativity value of 4.0, and hydrogen would be 2.1. This larger number, 4.0, tells you that fluorine wants to attract more electrons, or more of the electron cloud. So just based on these numbers, we know that fluorine would have the partial negative charge, and hydrogen would have the partial positive charge. Here's another way of depicting bond polarity with the Greek symbol delta. So delta positive for H, delta minus for fluorine. The last way would be with an arrow. So the arrow is always pointed to the more electronegative end of the bond. Now, if you somehow forget that, or you're just a little bit confused, just take a look here at the tail end of the arrow. You see that it looks like a plus sign. So this right here tells you that hydrogen has the partial positive charge. Here are a couple of definitions regarding bond polarity. So if you have a purely covalent bond, then those electrons in that bond are being shared equally between the two atoms. If one atom is a little bit more electronegative than the other, then you would have a polar covalent bond. There's an unequal sharing, so there would be a dipole moment in that bond. So when you see the term electronegativity, think of an atom that wants to attract electrons to itself. Now make sure you memorize this trend here. When you go from left to right across the period in the periodic table, electronegativity is going to increase. When you go from top to bottom, electronegativity will decrease. So because of that, fluorine, which is found in the upper right-hand corner of the periodic table, that'll be our most electronegative element. Francium, on the other side, opposite corner, would be the least electronegative. So to figure out if a bond is polar or not, we have to take these electronegativity values, find the difference between the two of them, and then figure out if the bond between those atoms is polar or not. Here you could see that generally speaking, going from left to right, the electronegativity is increasing. The electronegativity values that I would memorize would be that of fluorine, because it has the highest, francium, because it has the lowest, and hydrogen, because it seems to be the oddball here in the first column. So again, to figure out if a bond is polar or not, you'd have to take these electronegativity values, subtract them, and then figure out if the bond is polar. So now, knowing the electronegativity trend and having that figure in the previous slide, arrange these elements in order of decreasing electronegativity. So the last element in the arrangement should have the smallest electronegativity value. So press pause, take a look at your periodic table, use those trends, and when you're ready for the answer, click play. Okay, so here's our answer. If you didn't have the figure in front of you, just remember the trend. So going from left to right, electronegativity would be increasing. And going down the column, the electronegativity would decrease. This is one set of electronegativity differences that you could use to label the different types of covalent bonding. You could see when the difference is really close to zero, you pretty much have a pure covalent bond or even a nonpolar covalent bond. But as that difference increases, you're getting closer and closer to a bond that is ionic. So again, this is one way of figuring out the type of covalent bond. These divisions are pretty much arbitrary, but I'm going to show you an easier way to memorize. So this picture is pretty much the same thing in regards to the information from the previous slide. Here, this line graph shows you electronegativity difference. So you are subtracting the values, the En values that are designated on the different atoms, and then you'd use that difference to figure out the type of covalent bond which is found between those two atoms. So this is what I would do. I would just memorize 0.4 and 2.0. Anything less than 0.4, I know that the bond is nonpolar, a nonpolar covalent bond. Generally speaking, the electrons are going to be shared equally. If the electronegativity difference is larger than 2.0, then I know I'm looking at an ionic bond. Everything else would fall in between 0.4 and 2.0. And so if I have a delta En that falls in this part of the line, then I know that the bond is a polar covalent bond. So again, I would just memorize 0.4, 2.0, and see where this delta En would lie in this number line. If that number line was too confusing for you, then you don't need to memorize that. If you prefer something like table 10.1 for you to figure out the type of covalent bond, then go ahead and use this. Here we have 6 pairs of atoms. You have to figure out whether the bond that's formed between them are covalent, polar covalent, or ionic. So you know the formula. You have access to the electronegativity values, and you have table 10.1 to help you figure out if the bond is covalent, polar covalent, or ionic. So please pause the video, work everything out, and when you're ready for the answer, click play. Here you go. So I'm not going to show you the math. I'm going to assume that you guys know how to subtract. So take those differences and compare them to what's laid out for you in table 10.1. And here you could see the types of bonds between the pairs of atoms. Now we're introduced to dipole moment, which is still looking at bond polarity. You already know that a dipole has a positive end and a negative end, but we're not going to take a look at Coulomb's law. We're going to look at this equation here. Dipole moment is designated by the Greek letter mu, and it's equal to charge times distance. So you could see the differences here between this equation and Coulomb's law. Not only is charge directly proportional to the dipole moment, but also the distance. Another thing that you need to know is that this value, the dipole moment, is measured in dBs. Table 10.2 compares the electronegativity differences and dipole moments between 4 different types of molecules. So starting with Cl2, we know that the bond between these two chlorine atoms is purely covalent. And as we go down this column, that bond is becoming more and more ionic. So LiF is actually an ionic compound. Now let's take a look at delta En. We see that it is increasing. And now compare that to dipole moment. That's also increasing with the increasing electronegativity difference. So calculating dipole moment really just involves multiplying the distance between a proton and the electron that's being removed and the charge. One other thing that you need to know is the conversion factor between dBi and Coulomb times meter. So if you are looking at the charge of something, so let's say an electron, normally you would think of -1. Well, that -1 just tells you the magnitude of the charge. That charge is actually equal to 1.6 times 10 to the -19 coulombs. If you see a -2 charge, well, that means 3.2 times 10 to the -19 coulombs. Okay. Also, don't forget the conversion factor between picometers and meters. So in this equation, you just multiply these two values together and then convert this value to dBis. So here our answer is 6.2 dBis. And this is the theoretical dipole moment. When you go back to the previous chapter that had limiting reactants and you needed to figure out theoretical yield, actual yield, and percent yield, well, you could see similarities between that and calculating dipole moment. So calculating percent yield from a previous chapter, that's like calculating percent ionic character here. So we're going to be dividing out two different values, the actual dipole moment, and divide that by the theoretical dipole moment. So that's like saying actual yield divided by theoretical yield. If you multiply that by 100, you get percent yield. So we're going to use this similar equation to figure out the percent ionic character of a compound. So let's do that now by using the information from the previous problem. We have a diatomic molecule that has a bond length of 130 picometers. It has an actual dipole moment of 3.5 dBis. The theoretical dipole moment is 6.2 dBis. So what is the percent ionic character? Well, we take the actual dipole moment and divide it by the theoretical, multiply by 100, and we get 56% ionic character. Here you could see the relationship between percent ionic character and electronegativity difference. As electronegativity difference increases, the percent ionic character also increases. You could also see that there's no compound that has 100% ionic character. And actually, all of these compounds here, they are ionic, So with anything that has at least 50% ionic character, they would be considered ionic compounds. With this question, you're going to need the graph from the previous slide to answer. Here we're specifically looking at HCl with a bond length of 127 picometers and a dipole moment of 1.08 debye. So take a look at the figure from the previous slide to estimate the percent ionic character for HCl. So pause the video, take a look at that, and when you're ready for the answer, click play. The answer is letter B. Hopefully you guys know how to read a graph. The HCl did not quite reach 25%. So to figure out if it's A or B, 5% or 15%, divide up that bottom segment in half so that the division that you made represents 12.5%, and you'll see that HCl lies above 12.5%. So our estimate here is 15%. Now let's take a look in drawing out these structures. So there are some rules that we have to follow, but once we know how to draw Lewis structures, then we could figure out the shapes of these molecules. And again, we could use those shapes to figure out the physical and chemical properties of those molecules. So follow these rules in order so that you can draw the correct Lewis structure for each molecule. This order is a little bit different from the textbook, but I feel that this arrangement will get you drawing Lewis structures better and even faster. So the first step that I have for you here is figuring out the total number of electrons that you would need to draw out the structure. And you do that by adding up the valence electrons from each atom. Now, if you are trying to draw a polyatomic ion, you have to consider the charge magnitude of that ion. So let's say that your polyatomic ion has a +3 charge. You're going to have to deduct 3 electrons from your original total. If you have a polyatomic ion that's 2-, that means you need to add 2 electrons to your original total. Once you have that, then you can move on to the next step, which is drawing the skeletal structure. The least electronegative atom needs to be the central atom. You're not going to consider hydrogen. It's always going to be a terminal atom because it won't require a complete octet, just a complete duet. Once you have that skeletal structure, then you can distribute the electrons. Make sure that you are adding enough electrons so that each atom would have a complete octet or duet, whatever the case is. But make sure that you use all the electrons from step 1. After you've used all your electrons, but you see that some atoms don't have a complete octet, this is where you would need to draw out double bonds or triple bonds. To help you figure out the correct Lewis structures for different molecules, just follow these patterns. So for carbon, always, it has 4 bonds. It could be 4 single bonds, 2 double bonds, any combination of those multiple bonds. Just got to make sure that carbon has 4 bonds. With Oxygen, most of the time, it would have 2 bonds and 2 lone pairs. So again, that could be 2 single bonds or 1 double bond. It all depends on the molecule. So make sure to keep these patterns in mind when you're drawing out Lewis structures. Also, if a Lewis structure is given to you, just to make things simple, sometimes the lone pairs are left off of that structure. You have to make sure, you always have to keep in mind that lone pairs are actually there. Now let's say that you drew out your Lewis structure. And here we have SO2. You used up all the valence electrons, and each atom in the molecule has a complete octet. How do you know if what you drew is actually correct? Well, this is where we have our unofficial step 5, calculating formal charge. And here is the equation in doing that. For formal charge, you're going to look at one of the atoms and using the number of valence electrons, bonding and non-bonding electrons, you're going to figure out what the charge is for that atom in the molecule. So let's go through SO2, one atom at a time. We're going to look at this left-sided oxygen here, the ones that is double bonded to sulfur. Okay, if you have your periodic table, then you could figure out how many valence electrons oxygen would have. You could see that it's in the 6th column, so it has 6 valence electrons. Now, this oxygen has 4 non-bonding electrons, and we could see that in our structure. It's got 2 lone pairs, or in other words, 4 non-bonding electrons. Now, how many bonding electrons does it have? You see that there is a double bond, so there are 2 pairs of bonded electrons, or in other words, 4 bonding electrons. Don't forget the 1/2, which is found in the equation. When we do our math, we have a formal charge of 0 for this oxygen. Now let's do the same thing for sulfur. It's also found in the 6th column, so the number of valence electrons is 6. We see 2 dots in our structure, so it's got 2 non-bonding electrons. It's got 3 pairs of shared electrons. So that's why we're writing the number 6 in the equation for the number of bonding electrons. When we do our math, sulfur has a formal charge of +1. Now let's do the oxygen on the right-hand side. Valence electrons is 6 again. We see 6 dots, so 6 non-bonding electrons, or 3 lone pairs. We only see 1 line connecting the oxygen to sulfur, so there are 2 bonding electrons. And when we do that math, we have a -1 charge for this oxygen. Okay, so here are our formal charges. Now we know that SO2 is a neutral molecule. So here in this example, when we add up all of our formal charges, it adds up to 0. We already know that we used up all the valence electrons. Each atom has a complete octet, so this Lewis structure can work for SO2. Now, if you have a polyatomic ion, then the total of these formal charges needs to equal the overall charge. So make sure you keep that in mind when you're drawing out the Lewis structures for a polyatomic ion. Now try these 6 species in drawing out the Lewis structures. Pause the video and go through all the steps, including the 5th unofficial step, which is formal charge. When you're ready for the answers, click play. Here are the Lewis structures for this set. It's okay if you got some of these wrong. Again, practice is really important here. So I'll show you how to draw out carbon dioxide and the ammonium ion. If you got any of these wrong, try again. At least now you have an idea of what the answer should be, but start from the beginning.
So we're going to be drawing the Lewis structure for carbon dioxide, CO2. We're going to follow the steps that are in the slides that I gave you. So first step, count how many total valence electrons that we're working with. So for carbon, that's 4 valence electrons. Oxygen, we have 6, but we have 2 of them. So when we add all that together, we end up with 16 valence electrons. Okay, first step down. Second step, draw out the skeletal structure with the least electronegative atom in the middle. So that's carbon. So we have C, and then O's on either side. Okay, at this point we used 4 electrons because we drew 2 lines. We drew 2 single covalent bonds. So we have to add 12 more valence electrons. Okay, so let's do that. We have 2, 4, 6, 8, 10, 12, 14, and 16. Okay, we used up all the valence electrons that are available to us. Now let's see if we have complete octets. For this oxygen here, we have 8 electrons. We have 2, 4, 6, 8. Same thing for this electron. We have 8. This oxygen, we have 2, 4, 6, 8 electrons. But for carbon, we only have 4 electrons because we have only these 2 single bonds associated with the carbon. So that's a problem. Carbon definitely has to have a complete octet. So what can we do? Maybe we can move a lone pair on one of the oxygens and place it on carbon. Well, let's see what happens when we do that. Okay, so this oxygen still has a complete octet. We didn't do anything to it. Here for this oxygen, how many electrons are there? 2, 4, 6. Okay, that's already no good. But we can see that when we moved an electron pair, a lone pair, to carbon, it increased our tally. We have 2, 4, 6 electrons now for carbon instead of 4. So did moving a lone pair of electrons from one atom to another help us in any way? No, not really. So try not to move a lone pair from one atom to another. If you find that an atom is deficient in electrons and you use up all the electrons, it's better if you form another bond. Okay, look at what we did here. We took one of the lone pairs and now we're sharing it with carbon. So now let's count how many electrons are associated with this oxygen. 2, 4, 6, 8. We still have our complete octet for oxygen. Same thing for this one too. We didn't touch this, so this oxygen on the right-hand side still has 8 electrons. Now look at what we did for carbon. We still increased it to 6 from 4. So that's what you need to do. You have to take one of the lone pairs and turn it into another bond. So this is going to be our structure for carbon dioxide. We use up all 16 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16. And all of our atoms have a complete octet. Now, are we done here? No, we still have to figure out formal charge. So we're going to look at this Lewis structure. That's our best one right now. Now let's make sure that it's our best one. So let's figure out the formal charge for oxygen. It doesn't matter which one because the connectivity is the same. This oxygen is doubly bonded to the carbon, and it also has 2 lone pairs. And you can say the same thing for this oxygen, and because of that, we just need to find the formal charge for one of the oxygens. Okay, so first, how many valence electrons does oxygen have? You look at your periodic table, and you should know that it is 6. Now we're going to subtract out the non-bonding electrons in our Lewis structure. So these are our lone pairs. We have 4 of them. Now how many bonding electrons are there for this oxygen? We have 4, because we have a double bond connecting oxygen to carbon. We're only going to take half of those. So when we do the math, we should end up with a formal charge of 0. Now let's do the same thing for carbon. How many valence electrons does carbon have? Looking at the periodic table, you see that it's 4. How many non-bonding electrons does carbon have? 0. You don't see any dots in our Lewis structure. How many bonding electrons does carbon have? We have 8 because we have 4 lines that are connected to carbon. We're only going to take half of those. When we do the math, we end up with a formal charge of 0. So now we add up all our formal charges, come up with 0, and that is the charge for carbon dioxide. So make sure that you go through this entire process from beginning to end. You should start off with counting the number of valence electrons. Then you're going to try out different structures. Once you have the best one, figure out your formal charges. Make sure that your final sum of the formal charge is equal to the charge of the molecule. Okay, let's start drawing out NH4+ ammonium. So first step, we need to know how many valence electrons we're going to be working with. So looking at your periodic table, you should see that nitrogen should have 5 valence electrons. Hydrogen would have 1, but since we have 4 hydrogens, we got to multiply that by 4. Also, we have a +1 charge for the ammonium ion. That means that 1 electron was taken away. So we have to do that in our tally. So we're only working with 8 valence electrons. Okay, now step 2, let's draw out our skeletal structure. Because hydrogen has to be the terminal atom, nitrogen is going to be our central atom. Okay, how many electrons did we use to make our skeletal structure? We used all our valence electrons. We used 8. So this is pretty much it. This is our Lewis structure, except we need to draw brackets, and we need to have our charge outside of the brackets. Now let's double check and make sure by figuring out formal charge. We're only going to do the calculation for one hydrogen because all of the hydrogens are connected to nitrogen in the same way. So hydrogen has one valence electron. Looking at this hydrogen right here, how many non-bonding electrons does it have? It'll be 0. How many bonding electrons does it have? 2. We're only taking half. So all the hydrogens have a formal charge of 0. Now let's do the same thing for nitrogen. We already said that it has 5 valence electrons. We don't see any dots or any lone pairs, so the number of non-bonding electrons is 0. How many bonding electrons does nitrogen have? It's got 2, 4, 6, 8. We're only taking half. So our formal charge for nitrogen is a +1. So now let's add everything together. Our sum is +1, and that should make sense because that is the charge of this polyatomic ion.
These next few slides will test a couple of concepts at the same time. So here we have NH4+. We just saw the Lewis structure for it. In which period is the central atom located in the periodic table? So pause the video, take a look at your periodic table. When you're ready for the answer, click play. Okay, so our central atom here is nitrogen. Our other option, hydrogen, is usually drawn as a terminal atom, so our only other choice is nitrogen. And looking at the periodic table, you'll see that it's in the second row, or in the second period. Now do the same for H2SO4, or sulfuric acid. In which period is the central atom located in the periodic table? Press pause, figure out the structure, then take a look at your periodic table. When you're ready for the answer, click play. Okay, our answer here is the third row, or the third period. And that would make sense here because sulfur is our central atom. It's the least electronegative. If we don't pay attention to hydrogen, again, that's always going to be a terminal atom. So you might see this type of question later on a quiz or on an exam. You need to know how to draw Lewis structures to answer this type of question. Here we have phosphoric acid. So considering what the central atom is, where is it located in the periodic table? Press pause to draw this out, figure out where the central atom is located, and when you're ready for the answer, click play. Okay, so the answer is 3 again because phosphorus is our central atom. So why did I show you those 3 questions? Well, there are going to be some exceptions to the octet rule. With hydrogen, we know that it cannot form a complete octet. It'll form a complete duet. For an element like beryllium, only 2 bonds would form. Boron would be 3 bonds. There are also going to be others that would have an expanded octet. Okay? These elements are found in the 3rd period and below. They have enough empty d orbitals to hold more electrons, and so they would have expanded octets. So with the last 2 questions, with the sulfuric acid and phosphoric acid, the sulfur and the phosphorus can have expanded octets. So if you drew Lewis structures for those compounds that have more than 8 electrons around the central atom, you probably drew them correctly. Remember about the exceptions to the octet rule. So for elements found in the third row of the periodic table and below, they would have enough empty d orbitals to have more than 8 electrons in its valence shell. When you go through the first step in writing out Lewis structures, you might come across some molecules that would have an odd number of electrons. So those are called free radicals or radicals, and there would be just one unpaired electron. So that's the case for NO here. Also, don't forget about some of the elements that would form incomplete octets. Another concept that we're going to dive into so that we could draw the best possible Lewis structures is called resonance. So here, the electrons are delocalized in the molecule. And that just means that electrons are not fixed on any particular atom. They can move throughout the molecule. And in doing so, the molecule would be more stable and have lower potential energy. We're going to take a look at SO2 again. Several slides back, we only saw one Lewis structure, but here we could see that there are 3 correct Lewis structures for SO2. When you take a look at it very carefully, all 3 of these structures, you could see that the electrons are moving throughout the molecule. The connectivity of these atoms remain the same. So sulfur is still the central atom. And it's not like the oxygens are moving from one side to the other. Try to picture nailing down these 3 atoms so that they don't move. What's moving throughout the molecule is the electrons. So these 3 structures here for SO2, they are called resonance structures. And these 3 structures, they all contribute to what's called the resonance hybrid. So that's just a combination of all 3 of these structures. Here we have 2 different Lewis structures of ozone, so that's O3. Again, picture these 3 oxygen atoms nailed down to a surface so that they don't move. The only things that are moving are the electrons. Okay, so we could take one of the bonds in this double bond, move these 2 electrons so that it becomes a lone pair on this left-sided oxygen. And to make sure that the central oxygen has a complete octet, we have to take one of these lone pairs here on the right-handed oxygen and make sure that they're shared by drawing a line. So we now have a double bond on the right-hand side. Okay, so these are 2 resonance structures for O3, ozone. The resonance hybrid for O3 is a combination of these 2. So it's not like, ozone goes back and forth between these 2 structures. It really is just a mixture of the 2. So there are some rules that you have to keep in mind when drawing out resonance structures. Like I mentioned before, the structures have to have the same connectivity. So you can't change out the central atom when you're drawing out resonance structures. It's only the electron positions that can change. The first step in drawing out Lewis structures involves you counting the number of electrons you would need to draw out the structure. Well, resonance structures would use the same number of electrons. In regards to expanded octets, the same rule applies. Any elements in the third row or below would have an expanded octet. And following through with our unofficial step 5 regarding formal charges, the sums of the formal charges in each resonance structure should be the same. So let's start drawing out some resonance structures. Our first step is to draw out our Lewis structure. So here we have NO3-. This is the nitrate ion. Our Lewis structure here has complete octets for the nitrogen and the 3 oxygens, and formal charges have been assigned. Okay, so this oxygen right here, it's got a formal charge of 0. Now let's start moving electrons around. You're going to pick one atom that has a negative charge. So let's take a look at this oxygen right here. And we're going to move this lone pair towards the nitrogen. So in other words, we're going to make this lone pair into a bonding pair. So now we're going to have a double bond here. Now we have to be very careful because nitrogen is not found in the third row or below. So nitrogen cannot have an expanded octet. Okay, so we have to keep that in mind. If we do have an atom that's in the third row or below, then, you know, for, like, let's say that this is phosphorus, it can have 5 pairs of bonding electrons. So now, when we move that lone pair over, when we move this lone pair over so that it could be a bonding pair, we'd have to take one of the bonds in the double bond and make it a lone pair in this other oxygen that has a formal charge of 0. So now let's take a look at our resonance structure. Our right-handed oxygen now has a formal charge of 0, and our left-handed oxygen has a -1 as a formal charge. Now you could do this again, like if you start off here, you could form a double bond with this middle oxygen. Okay, but then this double bond needs to disappear, just so nitrogen can have a complete octet. Okay, so nitrate has 3 resonance structures, and when you draw these structures out, make sure that you have a double-headed arrow in between the structures. There are several ways for you to draw out resonance structures, but follow these tips so that you could draw the best structures. Okay, so better structures would have fewer formal charges. So the more zeros that you have in your molecule, the better. If you need to have formal charges, make sure that they are small. So they got to be closer to 0 as possible. Now, if you have to have negative formal charges, make sure that those negative charges are on the more electronegative atoms. So going back to the previous slide with the nitrate ion, you don't want to draw a structure where nitrogen would have a negative charge. That doesn't make any sense because oxygen is more electronegative than nitrogen. Now looking back at the nitrate ion resonance structures, all 3 of those structures contribute to the resonance hybrid equally. Why? Because in all 3 structures, the formal charges are the same. There's one atom that has a formal charge of 0, the nitrogen would have a +1, and 2 oxygens would have -1 values. Now here we have sulfuric acid, H2SO4. You could see that all the valence electrons have been used in drawing out these 2 Lewis structures. This one on the left-hand side, you could see that all the atoms that are not hydrogen have complete octets. But this one on the right-hand side, we could see that sulfur has an expanded octet because it's found in the 3rd row of the periodic table. Now, which structure contributes more to the resonance hybrid? The answer is this one on the right-hand side. Why? Because of the formal charges. All of the atoms in this structure have a formal charge of 0. So again, both of these resonance structures contribute to the hybrid, but the one on the right-hand side contributes more to the hybrid because of formal charge. Now let's test for understanding. We have a polyatomic ion here, SCN-. Which structure out of the 3 choices given is not a resonance structure of this polyatomic ion? So pause the video, look at your choices very carefully, and when you're ready for the answer, click play. Okay, so our answer is letter B. This is not a resonance structure because you could see that the connectivity has changed. Originally, carbon is our central atom. With letter B, it got switched out for nitrogen. So remember, in resonance, only the electrons are moving around, not the different atoms. Here we have the cyanate ion, OCN-, and we have 3 resonance structures for this polyatomic ion. Using formal charges, you have to figure out which resonance structure would contribute most to the hybrid structure. So please pause the video, figure out the formal charges for all of the atoms in all 3 structures, and then figure out which one would contribute the most to the hybrid. When you're ready for the answer, click play. So it's probably easier to set up a table. Again, don't forget the formula for formal charge. If you haven't memorized the number of valence electrons for oxygen, carbon, and nitrogen yet, make sure that you take a look at the periodic table. So here are those values. Next, we got to figure out the number of non-bonding electrons. So we got to count the dots that are around each atom. And here they are. Next, we have to count the number of bonding electrons and then divide that by 2. So here are those values. When we do our math, here are the formal charges for each of the atoms in each resonance structure. Okay, so now which one is going to contribute the most to the hybrid? Well, we got to think back to the tips in writing out the best resonance structure. So one of the tips is that we want all the formal charges to be 0. Okay, that doesn't work out for us here because this is a polyatomic ion, so overall it's going to have a -1 charge for the cyanate ion. So we can't have all of these formal charges be 0. Okay, so let's move on to the next tip, which is if we have to have formal charges, they got to be as close to 0 as possible. So considering that, A and B are at a tie, with one charge being -1 and the rest of them being 0. We can automatically cross out form C, resonance structure C, because we have a +1 charge and a -2 charge. So that's something that we don't want. Now the last tip is if we have to have a negative formal charge, it's got to be on the more electronegative atom. So the one that wins is form A, because the -1 formal charge is on the oxygen. So all three of these structures contribute to the hybrid, but form A contributes the most. So try these out, pause the video, draw out all the resonance structures for each of these 4 compounds. When you're ready for the answers, click play. So here, with our first question, we're looking at the Nitrates Ion, which we've seen before. So here it is, all 3 structures. You could see that the double bond is moving from one oxygen to the other. And also the number of lone pairs are changing for each oxygen. Okay, so remember that. The connectivity remains the same, it's just the position of the electrons would be different. Also, when you figure out formal charges for each of the atoms in each resonance structure, you'll see that when you add up all those formal charges, they'll add up to -1.
We're going to be drawing out the resonance structures for NO2-, which is nitrite. So here we have the number of valence electrons already. So now, next step, let's draw out the skeletal structure. So N is going to be our central atom. We already used 4 valence electrons in drawing out our skeletal structure. So let's fill in the other 14. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. We have all 18 valence electrons on our structure. Let's see if we have complete octets. Both oxygens are good, but nitrogen, it's missing 2 electrons. So we're going to have to rewrite this somehow. In an earlier exercise, we saw that turning 1 electron pair into a covalent bond will do the trick. So let's change this lone pair here. Okay, we have 8 electrons here for this oxygen, 8 electrons for this oxygen, and 8 electrons for nitrogen. Okay, let's check formal charges. This oxygen is a 0. This is a -1. Nitrogen would have a formal charge of 0. So I know this because I've done this many times. You go ahead and go through all the motions, all the calculations, and see for yourself that we have 0, 0, -1. Okay? So now to complete this, we're going to need brackets. And remember, we're dealing with a polyatomic ion, so we need to have a minus charge here. Yeah, minus charge. So that's one Lewis structure. Remember, we're dealing with resonance, so we're going to need our double-headed arrow. And now we're just going to move the electrons. We're going to keep the same connectivity. And basically all you're doing is changing where the double bond is and how many lone pairs there are for oxygen. So here's our double bond. That means this left side oxygen would have 3 lone pairs. Nitrogen still has 1. Now on the right hand side we have 2 lone pairs of electrons. We still need the brackets and we still need our charge. This oxygen here on the left hand side would have a formal charge of -1. This nitrogen 0, and this oxygen is 0. So you can see the number of valence electrons are the same in both forms. The formal charges are the same in both forms. We have CH3NO2. We're going to draw the resonance structures for this compound. We know that this compound has 24 valence electrons. So now let's go ahead and draw out the skeletal structure. Carbon is going to be in the middle. It's the least electronegative atom here. And we know that hydrogen is supposed to be terminal. So let's just draw that portion out right now. Okay, so now we're left with nitrogen and oxygen. Out of these two, oxygen is more electronegative, so that means that nitrogen is also going to be a central atom. Okay, so how many electrons did we use to draw out this skeletal structure? 2, 4, 6, 8, 10, 12. All right, we got to add 12 more electrons. I'm going to add them to the oxygen. Obviously, we can't add any to the hydrogens. And carbon, as you know, should only have 4 bonds, so we're not adding any more electrons to carbon. So let's go ahead and add the remaining electrons to oxygen. Okay, now we used up all 24. Now let's figure out the formal charges. So you're going to go ahead and do the math. I already know what the formal charges are, just from practice. With hydrogen, they're all going to be 0. Carbon is also going to be 0. So we're going to focus on the NO2 portion of this compound. So again, from practice, I know that a singly bonded oxygen with 3 lone pairs has a formal charge of -1. So -1, -1. Nitrogen here has a formal charge of +2. Now if we add all them together, we come up with 0, and that should make sense because we have a neutral molecule. But look, we have a problem. Nitrogen only has 6 electrons associated with it. It's going to need 2 more to have a complete octet. So what is it that we need to do? We got to take a lone pair from an oxygen and bring it over closer to nitrogen. That was one of our rules for resonance structures. Find an atom that has a negative charge and move those electrons closer to a positively charged atom. So to do that, we'll rewrite this. Okay, so let's move this lone pair over. So we'll have a double bond here. So we have 2 lone pairs for this doubly bonded oxygen. We still have 3 lone pairs for the singly bonded oxygen. Now let's figure out formal charge. This singly bonded oxygen is still -1. This doubly bonded oxygen is now 0. This nitrogen now is a +1. Also, it has a complete octet. So this Lewis structure can work. When we add up all the formal charges, again, we come up with 0. The negative formal charge is with our most electronegative atom, which is oxygen. That's why this Lewis structure can work. Now let's draw the other resonance structure. So we're going to need our double-headed arrow. The CH3 portion is going to remain the same. Again, our connectivity is going to be the same. We're just going to move the electrons around. So the doubly bonded oxygen was over here. Now we're going to move it over to the top. So we have 2 lone pairs for the doubly bonded oxygen, 3 lone pairs for the singly bonded oxygen. If you work out the formal charges, again, the sum of the formal charges would be the same.
Okay, so here are the 2 resonance structures for CH2N2. We have formal charges of -1 for the singly bonded oxygen and +1 for the nitrogen. Okay, so when we add these 2 formal charges together, they add up to 0, which makes sense because our molecule is neutral. Now, which one contributes to the resonance hybrid more? The answer is neither. Both contribute to the hybrid equally. Why? Because if you take a look at nitrogen, it has a formal charge of +1 in both resonance structures. And for the oxygen having the other formal charge of -1, you'll see that formal charge on the left-hand side and on the right-hand side. So these are both equal. Let's check for understanding. Which one of these molecules would you expect to be a free radical? So think back to what a free radical is. Pause the video, figure out what the answer is, reason it out, and when you're ready for the answer, click play. Okay, so the answer is letter D. It's the only one that has an odd number of valence electrons. It's got 13. CO has 10 valence electrons, and carbon dioxide and dinitrogen oxide would have 16. Which of these molecules would have an expanded octet? Pause the video to figure it out, and when you're ready for the answer, click play. The answer is letter B. Out of all of these central atoms in this set, phosphorus is the only one found in the 3rd row of the periodic table. Carbon and nitrogen are found in the 2nd row, so they cannot have expanded octets. Try drawing out the Lewis structures for these 2 compounds. The steps are the same, except here the central atoms can have expanded octets. So pause the video, work it all out. When you're ready for the answers, click play.
Now we're going to draw out XeF2. It's got 22 valence electrons, so that's how many we're going to work with. Let's draw out our skeletal structure. Xe is going to be in the middle with fluorine on either side. Fluorine is the most electronegative atom. So we used 4 electrons already. Now we need to add 18 more. So we have 2, 4, 6, 8, 10, 12, 14, 16. What are we going to do with the rest? We got to add them to our central atom. So that was 16. We need 6 more. 18, 20, 22. This is our Lewis structure for XeF2. If you find Xe on the periodic table, it is below period 3, so that's why it can have an expanded octet.
Here is the Lewis structure for phosphoric acid. The formal charge calculated here is for the phosphorus because we've already seen the formal charges for hydrogen and oxygen with 2 lone pairs. They're all 0. We've seen the work for it. So now here's the work for phosphorus. It's got 5 valence electrons, no non-bonding electrons, so that's why our value here is 0, and 10 bonding electrons. So when you do the math, the formal charge for phosphorus is 0. Now we're going to take a look at bond energy, and that's how much energy is needed to break a bond, and specifically 1 mole of that bond in the gaseous state. We could use calculated bond energies to figure out the delta H of a reaction. Okay, you're gonna have to memorize an equation to figure out this delta H reaction. And what you have to realize is, again, it takes energy to break a bond, so that is an endothermic reaction. But remember that in forming a bond, that is an exothermic reaction. Forming bonds would lower the potential energy, and so that's why energy is released. Let's take a look at a couple of trends first before we do some calculations. So you can compare bond energies in a set of bonds, but they have to be comparable to begin with. So if we take a look at this bullet point here, you could see that carbons, 2 carbons, are joined by covalent bonds. And like we were saying before, if you have a triple bond, that'll be the strongest bond in the set, and a single bond would be the weakest. So on an exam or on a quiz, if we ask you to compare or to rank bond energies, there has to be some similarities in the atoms being bonded together. Okay, so you could do the same thing with carbon bonded with nitrogen. The same trend can be seen. Carbon that's triply bonded to nitrogen will have the largest bond energy. If they are singly bonded to each other, then you'll have less energy. Okay, now in regards to distance, or in other words, atomic radius, those atoms that have a smaller radius would have a stronger bond. So if you take a look at fluorine and going down that halogen column, you can see that fluorine is the smallest atom. So more energy is needed to break this bond between bromine and fluorine. If you compare that to 2 bromines, bromine is the largest one in the group, so you could see it requires the least amount of energy to break this bond. Okay, so here is the formula in figuring out the delta H reaction in regards to bond energy. Now, this is a little bit different from what you were used to before. Whenever you saw delta, that was final minus initial. But here, we're saying bonds broken, the summation of bonds broken, plus summation of bonds formed. Now remember, to break bonds, you need to add energy. So that is an endothermic reaction. Forming bonds is an exothermic reaction. And remember why bonds form in the first place. The potential energy would decrease and form a very stable environment. So when that's happening, energy is being released. Here in table 10.3, we have average bond energies. You don't need to memorize any of these, but you do have to be careful when you have a C that's doubly bonded to an O. Yeah, it has a value of 736 kilojoules per mole, but take a look, it has an asterisk. Why? Because if you're looking at carbon dioxide, then those two bond energies would each be 799 kilojoules per mole. Okay, so make sure you keep that in mind. You could also see the trends that we were talking about before. So let's take a look at nitrogen bonded with another nitrogen. If there's a single bond, we can see that it's the weakest of the set. Then it's the double bond and the triple bond being the strongest in the set. Now let's test for understanding. We have a reaction between hydrogen and oxygen to form water, which is a highly exothermic reaction. Which statement is true of the energies of the bonds that break and form during the reaction? So pause the video, read these three statements very carefully, make your choice, and when you're ready for the answer, click play. So the answer here is letter B. The energy needed to break the required bonds is less than the energy released when new bonds are formed. Now, if all of this is too wordy for you, then go ahead and use the equation and add values so that you can understand these choices better. So here's the equation that we need so that we could understand these choices better. Okay, so remember, when bonds are being broken, that is an endothermic reaction. So those delta H values that you saw in that last table, those delta H values would be positive. With bonds being formed, so when products are being made, those delta H values in the table would now be negative. Okay, because energy is being released. All right, so now let's say that our delta H for the reaction is negative 1,000 kilojoules. Okay, the reason why we have a negative value here is because in the problem it says that the reaction is highly exothermic, so we're going to need a negative value for delta H reaction. Now, what two numbers are needed so that when we add them together, we come up with negative 1,000 kilojoules? Well, there are many possibilities there. Here's one. Positive 5 plus negative 1,005 kilojoules. Okay, so we could see that the value for the bonds being broken is smaller than that of bonds being formed. so letter B makes sense. You could add another set of numbers. Still sticking with negative 1,000 kilojoules, we could do this. Same thing, we come up with negative 1,000 kilojoules. The energy needed to break the bonds on the reactant side is less than the energy released when new bonds are being formed on the product side. Okay, so if you ever encounter a problem like this on the exam or on a quiz, put in numbers in this equation so that you could understand the choices and even the problem better. So here we have a combustion reaction. It's already balanced. We're going to use the bond energies from table 10.3 to figure out the delta H reaction. Okay, so let's do this one together. My suggestion to you is to draw out the Lewis structures for all four of these compounds. And here they are. Okay, I didn't put a coefficient of 2 here for the H2O and 4 for the H2 because it's easier to see how many bonds you actually have if you draw everything out. Once you're used to this type of problem, then you could use shortcuts and have coefficients here. Okay, so have table 10.3 handy so that you know what the bond enthalpies are. Okay, here's our equation. Summation of bonds broken plus summation of bonds formed. Remember, here with bonds being formed, those values in table 10.3 would now be negative. Okay, all right, so this term right here, 4 times 414, that refers to the 4 CH bonds that are singly bonded. With this 4 times 464 kilojoules, you have 2 H2O molecules. And this is why it's important when you're starting out, draw out all of the Lewis structures. So here we could count 1, 2, 3, 4 oxygens bonded to a hydrogen with a single bond. And that value is 464 kilojoules. Then you would do the same thing for H2 and for carbon dioxide. And remember, you have 2 bonds of carbon with oxygen, and they are double bonds. So remember that little asterisk from in table 10.3? Yeah, remember that value is negative 799 kilojoules in this case. Okay, so you do the math, and our answer here, our delta H reaction, is positive 170 kilojoules. Here's another combustion problem, but this time with methanol. So use the bond energies, write out the balance equation, and draw out the Lewis structures so that you can calculate the delta H reaction for this problem. So pause the video while you do that. When you're ready for the answer, click play. Okay, so here is the balance equation for this reaction. I color-coded the products and the reactants just so you could see the math a little bit better. Okay, we're just going to go straight into the math. I'm going to trust that you're going to draw out the Lewis structures yourselves. For the most part, you should know, I mean, you could find it in the textbook, what the structures are for O2, CO2, and H2O. If you're not too sure about methanol, here is your clue. Okay, so let's go through the math together. Okay, so you could see that this carbon right here is bonded to the hydrogens. Okay, the carbon is bonded to these 3 hydrogens, so the 414 kilojoules needs to be multiplied by 3. Okay, now you could use your detective skills, figure out what these bond energies are referencing, and then you could figure out what the structure is for methanol. Okay, for carbon dioxide, don't forget that special value of 799 kilojoules. You have 2 molecules of H2O. So really you have 4 bonds of oxygen with hydrogen with a single bond. So when we do the math, our final answer is negative 641 kilojoules. Okay, do the same thing, figure out the delta H reaction for this balance equation. Press pause to draw out all the structures. Reference the table 10.3. Look at those bond energies. When you're ready for the answer, click play. Okay, so we're just going to go straight into the math. Remember to draw everything out, especially the ones with coefficients, so that you know the factor to multiply with the bond energies. So when you work everything out, our delta H for this reaction is negative 80 kilojoules. Next, we're going to look at bond lengths. So officially, that will be the distance between the 2 nuclei of the bonded atoms. Okay, we're not going to take a look at the electron cloud because you could see that there is overlap with the 2 electron clouds. So here, for our purposes, the bond length is the distance between the 2 nuclei. Now we're going to take a look at trends in bond length. Remember that when comparing triple, double, and single bonds are going to be the longest in the set. So when you're asked to compare bond length, there should be some similarities among the molecules in the set. Okay, thinking back to periodic trends, so in this case, atomic radius, when we move from left to right across the period, the atomic radius is going to decrease. So the same trend is going to be observed with bond length. When you go down the column in the periodic table, the atomic radius would increase. So we're going to see the same trend here with bond length. So just generally speaking, when you see longer bond lengths, they are also weaker bonds. There really is nothing for you to memorize here in terms of bond lengths, but you do have to understand that triple bonds are the shortest bonds and single bonds are the longest bonds. So if we take a look at this carbon-carbon set, okay, you could see that the triple bond would be the shortest in the set and the single bond would be the longest. The last type of bond that we're going to look at is the metallic bond. So remember that metals have very low ionization energies, so they could lose electrons very easily. So if you have a piece of metal, we're only dealing with metal cations in a sea of electrons. Those electrons are going to move throughout that metal piece. Okay, so here's our term again, delocalized. That means that electrons are not fixed on one particular cation. They're going to move throughout the metal. So here's a picture of sodium. So sodium cations in an electron sea. So the bonding results from the attraction of these Na+ ions for the delocalized electrons. Let's take a look at this bonding model versus what we see in reality. So here, like at this point, you should know that metals are very good electrical conductors. Now, why is that? Because of the delocalized electrons, because of the electron sea. Those electrons can move throughout the metal, so they are able to conduct electricity because of the movement of charged particles. Remember that heating up a substance would cause the molecules in that substance to move and vibrate faster. So when a piece of metal is being heated, the metal cations are going to vibrate more and vibrate faster. So because of that, it's going to be really hard for the electrons to wiggle through that metal piece. So as the metal is being heated, electrical conductivity decreases. In terms of heat conductivity, metallic solids can do this very well. So remember, as a substance is being heated, the vibrations of those molecules would increase. So in a piece of metal, not only are the metal cations vibrating, but the electrons are vibrating as well. So there would be a lot of collisions happening in that metal and kinetic energy transfer. And remember, kinetic energy is a form of heat. Looking back at Chapter 8, we know that when electrons jump from a higher energy level to a lower energy level, radiation would be released. And if that energy gap is the right distance, then the light that's being emitted can be part of the visible light spectrum. So with this bonding model, it's saying that delocalized electrons can absorb light and be excited to a higher energy level, and then emit that light when it relaxes to a lower energy level. And that's what we see in reality. Metallic solids reflect light. So with this type of bonding, the electron sea will flow throughout the metal, not just the metal surface. So if you need to pull the metal into thin wires or hammer them into thin sheets, the metal will not break because the bonds, the metallic bonds, will not break. So what do we see in reality? Metallic solids are malleable, so they could be hammered into thin sheets, and they are ductile. They could be pulled into very thin wires. Except for mercury, all the metals would have very high melting points and boiling points. Again, it's because of the electron sea. They are going to flow throughout the metal, so they'll wiggle their way through in between metal cations. So in order to break those attractions, a lot of energy would be needed. First to melt the metal, and then even more energy to boil the metal. When we're looking at the periodic table and comparing melting points based on that, we're going to see that the melting points would increase going from left to right. Now, why is that so? Because the charge magnitude would increase going from left to right. So you could see with Na having a charge of +1, Mg +2, and aluminum +3, you could see that their melting points increase. Again, because of the magnitude of that positive charge. Now think about what happens when we go down the column in the periodic table. The atomic radius and the ionic radius would increase as we go down the column. Now what's going to happen with the melting points? Well, they're going to decrease when you go down the column. And that should make sense because the further away the positively charged nucleus is from the electron C, the smaller the attraction. So then it'll be easier to break those bonds, and so less energy is needed to melt metals further down the periodic table.